Good afternoon, all my AP Chem students. Here we are again. I think this is podcast number 3. And today we're going to sum up a little bit what we did in section 15.4 with our titration. So we did our titration example and we got our titrate curve. We found our pH and we found our titration and the pH curve with a strong acid and a strong base. And we were taking the strong acid and then we were adding the NOH to it. And so we ended up with some sort of curve. If we just take a look a little bit at the summary here. So what we did is we had a strong acid plus a strong base. And so our strong acid, if we were taking a look at our XY axis again, over here was going to be our pH, and down here was the amount of OH that we are adding. And so when we were doing it in class, we found that inflection point in terms of our equivalence point, and we were down here because we know that a strong acid has a very low pH, and we are drawing our curve, and we were looking at that inflection point, and so we called this our equivalence point, and this is where we found our pH. So in this situation, we have our strong acid in our solution, we are adding our strong base to it, and we are recording the differences. So then, in the next situation, if I were to take a strong base and add a strong acid to this, you can see or hopefully understand that it's just going to be a flipped curve. So here's my pH. I'm still adding my OH, or I'm adding my, not adding OH this time, I'm going to add my HCl because I'm adding a strong acid or any of the strong acids that you know. And we are just going to get a flipped curve. You should recognize that if I have a strong base, the pH is going to be on this end of the scale, and as I go down, I'm going to have this inflection point. Now, what I want you guys to understand here is that in both these situations, my equivalence point or my pH can be 7 because I have a strong acid and a strong base, and you're making something neutral, which isn't going to change. However, this curve is going to change if I don't always have a strong acid and a strong base. And the other point that I want you to see is that you need to think about, if I have a strong acid, would you agree that I have a lot of hydrogen ions here, a lot of hydrogen ions here, and it's going to act like a buffer. It's going to take a long time for this pH to change. On the other side, the same kind of thing. I have a lot of hydroxide ions here. It's a great buffering material. The curve probably would be a little bit more like this, but it's a great buffering material, and it takes a lot of substance before you're going to see that change. So now we're going to take a look at the difference when we have a weak acid here with a strong base. And so some points here that it wants you to know that I have a reaction of OH, so I'm adding my base with a weak acid, and it's going to run to completion. Just like we talked about before, this OH is going to run to completion. This acid is going to continue to dissociate until there isn't any more hydrogen ions that this hydrogen proton here has an affiliation for. Then the acid remaining and the conjugate base formed are determined, and that's when I can start measuring my pH. So the initial concentrations are found after this goes to completion, which is what we did on every single step of our last titration before any dissociation of an acid occurs. Should make sense to you. This hydrogen ion is going to go here, keep dissociating until I have all this made into water, transferred into water. I still have some acid left over, and then that will just continue to dissociate. So the equivalence point is greater than 7 for weak acids with a strong base. This point is defined by stoichiometry, not by pH. So if we take a look at this graphically, you can see again that I'm going to have my pH, and in this situation it says I'm adding my OH, so I'm going to add this. And if I take a look at my situation with a weak acid, we know that the pH of that is a little bit on the higher end. So what happens is I have a situation where I have a flatter curve, and then it goes to where the basic situation is taking over. My equivalence point is here. It's going to be shifted. It's going to be greater than 7. However, this is taking a much shorter amount of time because I have a weaker acid. I have less hydrogen ions there for the buffering to take place. So the increase in pH, the pH is going to increase more rapidly for a weak acid than a strong acid because there isn't as many ions there. Keep in mind, my strong acid is way down here. It takes all this time to get up to here to this equivalence point, and its equivalent point is going to be down here. And so indeed the pH has increased for that weak acid. So again, we need to remember that we want this inflection when we exactly have the right number of acid and basic ions to get that pH to flip to the other side, and the leveling off is going to be due to the buffering. But it's the amount of acid, not the strength, which remember the strength is going to be my pH value, determines my equivalence point. And hopefully in our discussion yesterday, we talked a lot about that when we were developing our pH curves. So this is going to determine my equivalent point. And you can read more on this on page 707 if you have some more questions about it, and we can talk more about it in class. Now, again, the opposite of this is going to be true if I have a weak base with a strong acid. This inflection point is going to be very short because, again, I don't have as many ions there that are going to be able to buffer. Okay, well, there is the bell, so I'm going to have to stop this recording right at the moment, and I will return to you later in the day. Okay, good evening. I am not exactly sure what my last words were because I was recording this at school, and I'm at home now finishing this up, and it's intermission of the Wild Rangers game, and we're tied 2-2, so you might be watching that also with our own Derek Stepan playing up there. So we were talking about acids and bases, and we were talking about titrations, and I think I was making a point about that it's not the amount of acid, that it is the amount of acid, not the strength, that determines the equivalent point. And you have to remember that the equivalent point, let me grab a pen here, that the equivalent point that we need to take a look at is where the solution is exactly neutral, if you want to think of it that way. So it is an acidic pH, and it's the point where it's going to change over to a basic pH. And remember that this is caused because the leveling off, it's a buffer, and so we have that the acid is equal to the base at the exact concentration so that I can have this inversion of this pH at this equivalent point. So the reason that it's the amount of acid, because if you think of our burettes, and if I can draw a quick burette here, if you think about the burettes, and if you have them filled, that's a lovely burette, and they have them filled and they're dropping down into some sort of container down here, and you have some sort of titrant inside your burette, whatever it is, some sort of titrant. And so let's say that our titrant is some acid, okay? Well, if it's an acid, then I probably, well, actually this picture here is we are titrating with a base, and we are starting with an acid. So that would mean that I have an acid down here in my sample, and I am titrating here with a base, and I have some sort of indicator in here, probably phenolphthalein, that's going to tell me when I'm at my endpoint, meaning this equivalence point. And so if I have an acid down here, you have to think about the number of hydrogen ions that I have in here. Well, it is the amount that's in here, because if I have a smaller amount of acid, I have less hydrogen ions. If I have more acid in here, I have more hydrogen ions. Then that means I'm going to take more base to be able to get to this equivalence point. So it is the amount of the acid, not its strength, that's going to determine the equivalence point, because remember, we were talking about a buffering. And the more ions that you have down here, the greater the capacity it has for buffering. Okay, so that's titration curves, and hopefully those will make sense to you. There's one more little section that we're going to cover today, and this is on acid-base indicators. So we have two methods for finding an equivalence point, to finding those curves that we just talked about, using a pH meter and plot the titration curve. Later in the year, you will be doing a lab with that. It'll be one of your final labs that you'll be doing, and we will be calibrating our pH meter to plot our titration curves. And then the other thing is the acid-base indicator, and you already did that with the last lab that you turned in. And the two that you really have to make sure that you know is phenolphthalein, L-P-H-T-H-A-L-E-I-N. Don't ask me to spell that without looking at it. So phenolphthalein, you have to remember, is the indicator that if you add it to an acid, it's going to remain clear. And you saw that with your lab, that also, if you add it to a base, you get that nice, pretty pink color. And so it's a nice indicator to use because it's very easy to see the color changes. The other one that you also used was bromophenol blue. And bromophenol blue is the other one that's very common to ask questions about, that you're going to need to make sure you know what the colors are. And so in this one, you will also be doing a lab in this later in the year. This acid is going to turn yellow, and in the presence of a base, which you also saw in your last lab, is going to turn some sort of blue. Obviously, as it's going through an acid to a base, you're going to see some greenish color in the middle of here because you're not getting rid of all the acid at one point and adding just base. So you are going to have that intermediate. And then if you take a look in your book, which I can't tell you what page it is because I have all the books at school for you guys, for those of you that don't bring your books. So I have a different edition than what you guys have. But there is somewhere in your book, there's a huge picture of pH ranges of all different sorts of indicators. And you can see all the indicators have a different bandwidth. So if you take a look at phenolphthalein, it says it works best between a pH of 8 and 10. And bromophenol blue, if you look that up, it says it has a pH between 6 to 8 that it works the best. Well, all of these indicators are going to work the best in the middle of that pH band, which should make sense to you. And again, you would look at this chart to make sure what kind of pH you're testing. Obviously, phenolphthalein and bromophenol blue aren't going to work for something if you're testing pHs, on the other end of the scale from 0 to 3 or 0 to 4. So there's all sorts of acid-base indicators that you can use. All right, I hope this clears this up for you. I hope you have a great night and root on the Wild for us, and hopefully it'll come out with a victory. Have a great night.